Now, speaking of the inverse hyperbolic functions, it's quite synonymous in terms of form, to integrals yielding inverse trigonometric functions. Because in this case, the integrals will be the one that will, shall I say, yield an inverse hyperbolic function. Not that your integral will be an inverse hyperbolic function, but rather the answer to the integral will be an inverse hyperbolic function. Now, if you notice here, in terms of form, there's one big similarity to the integrals yielding the inverse trigonometric functions. One common thing that is noted here is that it's always a 1 plus the u squared expression. Now, or u squared plus 1, or we just interchange the two, and it's written under either a radical sign or with no radical sign. So in here, if it's the hyperbolic or the inverse hyperbolic sign of u, now you have in the denominator the square root of u squared plus 1. This should really be the form of your denominator. Now the du here that you see should represent the derivative of the u only. So if this is sine of x, or rather if this is sine squared of x, the du of that would be cosine x, because sine x is your u. So you need to have that complete cosine of x dx here for your du. That way you can answer this one, the inverse hyperbolic sign of u. So these two differs only by means of the sign that separates the u squared and the 1. So if it's a minus, you will have the inverse hyperbolic cosine. Now, the difference of the tangent or the inverse tangent, the arctangent function, is that your integral is 1 over 1 plus u squared, the arctan function. Now, if it's the inverse of the hyperbolic tangent, it's not a plus that separates the 1 and the u squared, but minus. And take note, class, this particular integral can have two possible answers. So, an inverse hyperbolic tangent is acceptable. The same thing with the inverse hyperbolic cotangent of u. Okay, as long as the form is like this. Now for the second, our answer for the inverse trigonometric function for the second is positive, whereas in here you could see that it's negative. Okay, and we interchange these two. Instead of 1 minus u squared, here in inverse hyperbolic second, it's 1 minus u squared. In trigonometric functions or inverse trigonometric function, it should be u squared minus 1. So similar in some way, we only interchange the terms, or there's a change in the sign. Okay, if it's inverse hyperbolic cosecant of u, it will also be negative, and instead of having the minus here, you have the plus. These are the 6 primary integrals, form of the integrals yielding these inverse hyperbolic functions. I say primary because it's not all the time, just like the inverse trigonometric functions, that it's 1 that is being added to u squared or 1 that is being subtracted from u squared. This one at times could be any real number. And there would be a different set of formulas somehow similar to this that we could use if it's not 1 that you see here together with the u squared expression. So we're going to look into those formulas. The manner we modify these primary formulas here is comparable to the way we modify the primary 3 formulas for integrals yielding the inverse trigonometric functions. So I will go to the next line below to show to you the formulas. You have it here. Okay, let me just decrease the size. So you can see here, if you have 1 over u squared, either plus or minus. So this means that it can either have plus here or minus a squared. The integral for this is the ln of the quantity u plus the square root of u squared plus minus a squared, those quantity plus c. How will you interpret this class? So if this is a plus that separates the u squared and the a squared, where a squared is any real number, it should also be a plus in here. You see here, you also have two choices, plus, minus. If it's a minus here, you should also have a minus here. Now, this is one formula, if you can recall, for the answer for the integral in which the form is comparable to integrals yielding the inverse trigonometric functions, an ln. But I suggested that it would be best to focus on an answer that is also by nature is also inverse hyperbolic, in this case hyperbolic function. In that case there, when we're discussing about inverse trigonometric functions, I suggested that you also focus on the answers that are related to it. So you also focus on the answer that yields an inverse trigonometric function. So it's the same thing in here. But it's important, class, that you also know this, because if it's a multiple choice type of exam or quiz, or if there's an ECE here, board exam, this would be the answers that would be provided in the choices. So you may wonder why is it an ln? But actually an ln can also be an answer, although we're so accustomed to having answers in the form also of the inverse hyperbolic functions. So having said that, if this is the form of your integral, class, this is your answer. Now, this will be your answer, the inverse hyperbolic sign of u over a. You take the square root of this a squared, so you make it as the denominator of the argument of your inverse hyperbolic sign. You use this answer if the operation that separates the u squared and the a squared is positive or plus. This is your answer if it's plus, like u squared plus a squared. So this should be your answer. If it's a minus, your answer should be the inverse hyperbolic cosine. So u squared minus a squared, this should be your answer. Okay, this is how you should interpret it. Your answers actually could come in 4 different forms, either this one, or this one, or this one, which can have either here a plus or a minus depending on the sign that separates your u squared and your a squared. Now, for this one, this would have been the inverse hyperbolic, the inverse hyperbolic second and inverse hyperbolic cosecond, both negative if we have here a 1. But in this case here, it's a real number. So this time you have negative 1 over a ln of. So the argument is complex in the sense that you have here the a. So you take the square root of this plus the square root of a squared plus u squared if you have plus here. If it's minus, you should also have minus here, divided by the absolute value of the u, or you simply divide it by the u, plus c. Now in here this time, you don't have the, it was not written here, the answer for a resulting inverse hyperbolic functions as well. Now there's a note here that you study pages 38 to 39 of the study guide, which is also indicated in your Canvas notes. So please check on that. That way you will know the alternative formula for this one, or an example, more examples on this particular use of the formula. Now, in here, you have 1 over a squared minus q squared. I've mentioned that if this had been plus, we have an arctan, or the inverse tangent. But since it's minus, then we have this answer here, which is in terms of the ln again. So please don't have the u in here because it should not be included then there's an error here. So it should only be 1 over a, the ln of a plus u over a minus u, absolute value of such, plus c. Now, you may wonder why, Miss Ali, why is it that there's really an absolute symbol here in the integral? Because it's not always class all the time that your integral will be indefinite. Integral that doesn't have limits. In the end term, your integrals will have limits already. And this is where the value of the ln should really be positive at all times. Because if you're going to process in your calculator any value in the ln which is negative, will result to an error. Your calculator will not be able to process that. That is why ln's should always be, or the argument of the ln's as much as possible should be positive. So that is why I place here absolute value, meaning even if it's negative, you have to use its absolute value, or you have to negate its negative sign. That way, you can have a real acceptable value for the quantity that you are determining, in which this is your answer. So that's the purpose of the absolute symbol for the ln. In cases wherein we're already given a definite integral. This one is an indefinite integral. Okay, so these are the other 3 formulas. Different from the first 6 primary formulas in the fact that your a squared could be any real number. In the 6 primary formulas, in here, it's always 1 that is paired with the u squared. Okay? Now, do you have any questions to this one? Anyway, it's all about the formula and understanding what you're going to place or substitute on the variables that appear in the formula and even the constants that appear in the formula. Now, let's have this example. You have 1 over 25 minus x squared, which is comparable to the form a squared minus u squared. By the way, I've limited the examples here, but in the actual document that was shared to you in Canvas, you have several examples. So please study the document that is shared to you. Okay, now your u here is of course x, and your du is dx. From that, you differentiate this, and your a is 5, the square root of 25. We know for 1 that this would yield either a hyperbolic, an inverse hyperbolic tangent, or an inverse hyperbolic cotangent, if this is 1. Okay, in this case, since it's not 1, you will have to settle for the ln answer. Okay, let me go to the top for you to recall what I just said. It's here. See this one minus can either be both an inverse hyperbolic tangent or inverse hyperbolic tangent, as I have mentioned, but that's 1. Wherein we subtract the u squared. In our example, it's not 1, it's any real number. So we cannot answer the inverse hyperbolic tangent or inverse hyperbolic cotangent. We will have to settle for the formula here on top, which is this. 1 over a, so that would be 1 over 5, the ln of a plus 5, or rather 5 plus u over 5 minus u. In our case, our u is x. Okay, we just use the formula to substitute or place in correct values or functions in the formula. So this is it. Okay? The second one is the inverse hyperbolic functions. This one would have been a arc sine, the arc second in the case of the inverse trigonometric function second, arc second, if this would have been a u squared minus 1. or a u squared minus a. In this case, it's not a minus, it's plus, but good that it's 1. So whenever you see a 1, then it must be following the formula for the 6 primary functions, yielding an inverse hyperbolic function. So your u here is 2x because this is u squared. The du of that is 2dx. So that's the purpose of the 2 in here, to complete the derivative of the u. Your a is 1. So then, actually, there's no need for you to multiply by u because this is already the 2 in here. So just paste in the 2, and then you have 1/2 outside. So there's a typo error here, class. So this is 2 over 1/2. But if there's already a 2 in here, your answer would just be a simple case of without this. Unless otherwise that there is no 2 in here. You get me? If there's a typo error here, that there's a 1 here, only a 1, then you need to introduce a 2 and there should be a 1/2 outside. Okay? Now, you see that we have an answer here, which is an ln. The answer that is being used here is the formula for the ln. Where is that? So, we have this one. Even if our a is 1, the ln formula was being used because doesn't mean, class, that it's 1, you cannot use the ln. The ln is still acceptable. It is okay for any real number for a squared, and 1 is any real number. So meaning, we can use that particular formula. So in this case, I'd like to go back to the formula. This one, the u squared plus 1. Okay, you have here a u squared plus a squared. This could be 1. Okay, pwede man na siya mag-1. So our answer could either be in the form of the ln or could be like this. Okay, the answer would be an inverse hyperbolic sine of u. Pwede gid siya, digto. But in this case, the answer that is used is in terms of the ln. But you can answer like this. You can answer the inverse hyperbolic sine of u. In that case, your u is 2x. Okay? But if this is 1, as I said, there should be a 1/2 inverse hyperbolic sine of 2x over 1. Because your a is just simply 1. Or if you use the ln, so if you use the ln, this is the ln that I'm mentioning about. Okay? If you use the ln, so you have the ln of u, which is 2x, plus the square root of 2x squared, which is 4x, plus 1, plus c. That is if we have u squared. Is it a u squared plus 1 or a squared plus 1? Let me check. Okay, so it's a 1. So it starts with a constant. So if it's a constant, it would be this formula that we're going to use, class. Not that one, but this one. Wait lang. We have an x. Okay. Did not see the x. So it would be this, class. Okay. We use this particular formula. We have an x outside. So we cannot use, I stand corrected, we cannot use the inverse hyperbolic sine answer because we have the u here. In the case of our example, it's the x. Let me clear my markings. It's the x here. So meaning it's comparable to this formula. So we just follow the formula for a 1 over u square root of a squared plus u squared, and it would be this. And we just substitute the things that we need to substitute. Okay? Just first and foremost, determine the u, the du, and the a. And then, of course, the form. Where does it fall? So this particular example forms on this form of the integral that will require this as the answer. if we take out the x here, if the x is not there, then it would be a simple, as I've said, inverse hyperbolic function of u. But since we have the x there, then we have this one. Okay? It's all about, class, knowing the formula that is applicable to the form of the integral that is given. What particular formula is applicable to this form? That formula is this. And then, of course, you follow whatever is the a and the u that you need to plug in on this particular formula. Now, any questions for the inverse hyperbolic functions? So just like the inverse trigonometric functions class, you need to be, however, very careful in terms of the form that you are comparing the given integral to you, That way you can use also the formula, because once you already know the form, the formula will just follow, because you need to only get the a, the u, and get the du, and that's it. You just simply plug in the a's and the u's in your formula. However, if the formula is wrong already, then everything, of course, will be affected. Okay? So this ends the inverse hyperbolic functions. We'll have a 10-minute break so that I can continue with the second to the last topic, which is rationalizing substitution. So you can stay there. Just have your cam off. Be back at 3:47. No. Yes, 3:47. Okay, we'll have a short break. Bathroom break for me and probably for some of you. So for our new topic, it would be on rationalizing substitution. So you really have to pay attention, because if you're going to ask me, this is the second most complex and lengthy procedure that you're going to do or apply in terms of evaluating an integral. It's a technique, another technique for you to learn. Okay, let me share my screen. Okay, I hope you can see my slide. Let me try again. I can see a notification that you see you are viewing my slide already. Can you see my slide? Rationalizing substitution.
Yes, ma'am.
Okay. I don't see a notification from my end. So good that you could see it. So in rationalizing substitution class, we'll be dealing with integrals that needs us to rationalize the expression prior to evaluating the said expression. So under method 1, so this is method 1, this is for integrals involving any nth root. Nth root meaning this could be square root, cube root, fourth root, fifth root, any nth root of the expression ax plus b. Now your variable x is multiplied to any real number and added to it is a real number b. Okay, the first thing that we need to do is we remove the radical sign, or as much as possible we do away with the nth root expression. Now, how do we go about getting rid of or doing away with this nth root here? Okay, so we assign u, or any variable that you want. You can assign w, v, or any variable. We assign u to this nth root expression that we have. So nth root of ax plus b. And for us to get rid of the nth root from your algebra, you need to raise, annotate. You need to raise the entire expression to n. Because if you raise this to n, this is already 1 over n. That gets rid of this particular radical expression. So in the process, your u here on the left side becomes u raised to n. And the expression that you have on the right side does not anymore have the nth root symbol. Okay? Interrupt me if you cannot follow. Okay, so what we do after we have done this one, we do the differentiation of our u, and we represent the x variable, the original x variable that we have in terms of this u. Differentiate and then substitute the expressions to our original integral. Now, I think that would be understood better if I'll go straight to the example. So you can see here, x over x plus 1 raised to 2/3 dx. This is the expression that you need to integrate. Your problem in this expression is this one, the x plus 1 raised to 2/3. And you want to eliminate the problem by using rationalization. Now, you assign u to this expression. So, we did that. U is equal to x plus 1 raised to 2/3. Okay? After that, just like what we have done here in the general procedure, you want to get rid of these 2/3. So in your algebra, how do you get rid of a rational exponent? You multiply it with the reciprocal of that particular, or you raise it rather to the reciprocal of that particular rational exponent. So I will raise both left side and right side of this equation to 3/2, the reciprocal of the 2/3 here, exponent of the quantity x plus 1. Because if we will multiply these two exponents, that would simply be equal to 1. Okay? I hope you can follow. So you raise your substitution equation. I'd like to call this substitution equation to an exponent which is the inverse of the exponent of the expression that you need to rationalize. So ang suli sining 2/3 is 3/2. Now, what happens if you do that? So now your u here on the left side becomes u raised to 3/2. I'd like to erase the markings that I have here. So it becomes now u raised to 3/2 here after you have raised it to 3/2, and this x plus 1 raised to 2/3 becomes x plus 1. A few seconds ago, I said from this equation that you will have, you will get an expression of your x, of your variable that is given in terms of u. So your x here is equal to, so you just transfer this one in here. That way you will have an x in terms of the u. So x is equal to u raised to 3/2 minus 1. You transfer the 1 in here. Okay? So first step, rationalize. This is what you did. Then get an expression of your variable in terms of the new variable that you used in rationalization. And then differentiate. So you differentiate what? This equation of yours, which is expressing rather your original variable in terms of the new variable u, which you use, which is also dependent on the letter that you want to use. So differentiate the left side and the right side of this equation. So you will have the x in the left side. This one will require power rule. So that would be 3/2 u raised to 3/2 minus 1, which is 1/2 du. The derivative of this negative 1 plus is 0. Okay, is 0. So you only have this one here. Now, I'd like to use a different font. What will you use? Or what's the use of this and this? The use of this x and this dx is for you to be able to replace in here this x by this and this dx by this. So this x should replace the x that you have here and this x that you have in here. Also, the dx should replace the dx that you have in here. So meaning you will change the variable of the original integral that is given to you to the variable that you have chosen when you first did rationalization. So look at what's happening here below. So your x is what? U raised to 3/2 minus 1. So it's in here. Okay? use a different color. So now your x is u raised to 3 halves minus 1. What about the dx? It's this. So you have 3 halves u raised to 1 half du. Okay? What about the x in the denominator? What will happen to the x in the denominator? So, this one. So you will have to change this x here by u raised to 3 halves minus 1. This entire expression is your x. And this is the one that you have here. Everything is raised to 2/3. Okay? So you replace the original variable by your new variable. The next step is, of course, you cannot integrate with such complicated expression as this. So what you do, you use your algebra. That way you simplify this expression. Okay? Now we will simplify. Now as you could see in here, another color will do. So you could see in here, in the denominator, you have a negative 1 plus 1 inside this parentheses. So you can cancel this because that would be anyhow equal to 0. Now, you have, in the process, if you have already canceled the negative 1 plus 1, you have now u raised to 3 halves raised to 2/3. So it's like this class, u raised to 3 halves or raised to 2/3. What becomes of it? Isn't this equal to u? Because this one is simply 1. So that should be u. So your denominator now is u. But take note, class, that this u could be cancelled, or we can take out this u raised to 1 half in here from this u that I have in here. So I'll take this out and I still have 1 half left in here. So that's the reason that you see this u raised to 1 half in your denominator. The 3 halves here was written before your integral because it's a constant. So these 3 halves that you have in here is these 3 halves now. The du remains in this side and the numerator is still u raised to 3 halves minus 1. Before I proceed, do you follow? Can you understand? Okay. So no questions, no raising of hands. I'll proceed. Now this is now your integral. Simplify further by dividing your u raised to 3 halves minus 1 by u raised to 1 half. You distribute u raised to 1 half to these two. What happens? 3 halves minus 1 half is 1. U raised to 1. And negative 1 divided by u raised to 1 half is negative u raised to negative 1 half. Look at it. Isn't this a lot simpler now to integrate than the original expression that you have? Without doing rationalization, it would be impossible for you to come up with this integral, which would simply be using power rule, because this would just be simply using power rule. Now, if you use power rule to this two, remember your integral is multiplied by 3 halves. So these 3 halves should be distributed to the answer of the two integrals here, which you will evaluate separately. Okay, so if you evaluate the u, that would be u squared over 2. If you evaluate u raised to negative 1 half, will be u raised to 1 half over 1 half. Both have 3 halves now. But this is not yet the answer. Before I proceed, do you have any question?
Miss,
Yes.
is it okay to repeat how we got u minus u to the power of negative 1 half?
Okay, take it. What you do is you distribute this u raised to 1 half as a divisor to these terms that you have in the numerator. Like u raised to 3 halves divided by u raised to 1 half. By rules of exponents, you're going to subtract the exponents. So 3 halves minus 1 half is 1. That is why you have u. This negative 1 divided by u raised to 1 half, this one will go up So the original positive exponent becomes negative. Do you follow?
Yes, yes, thank you.
Okay, so that's the reason why you have this answer now using power rule. Okay, I will proceed to the next slide. Some more questions. Okay, so I need to clear my markings here before we go to the next slide. So this is now the expression that we have. Remember, class, your original integral is in terms of the variable x. Now your answer here is u. So what do you need to do? You need to substitute back what this u represents in terms of x. What the u's here represent in terms of x. So that would be illustrated in the next slide. So this is your answer. Okay, and then it was simplified. This one was just copied, class. So this was just multiplied, and this one also. The 2 went up, so this becomes 3. So you have now this one. But this is not yet the answer. You have to substitute back the x, or you have to represent this u in terms of the original variable x. Where do you get this expression, by the way? Where was this taken? So I'll go back to the first slide first. Okay? Remember that this is your representation. Your u is equal to 3 halves, rather u raised to 3 halves equal to x plus 1 half. From in here, from this expression that you have, you'll get a formula or an expression in terms of x. So I just want to get the u in terms of x. So I need to get rid of the 3 halves here. What will I do? For me to get rid of the 3 halves, I will multiply it with its inverse. So it would be raised to 2/3. That way, this will be u. So you'll have now u equal to the quantity x plus 1 raised to 2/3. Again, remember this is your answer. In terms of u, your original variable is in terms of x. You have to return the u back to x because your original integral is in terms of x. Where will you get the expression that will replace u in terms of x? It will be taken from here. Okay? U, it has to be u. So this entire equation need to be raised to the reciprocal of the exponent of the u. So you have u equal to x plus 1 raised to 2/3. This is the expression that you see being substituted on the next line. U is equal to x plus 1, quantity x plus 1 raised to 2/3. So what are we going to do? Your answer here, u, will be replaced by this one. So 3/4, I copy the 3/4. So this one, 3/4, 3/4, check. What about this u? This is x plus 1 raised to 2/3. So quantity x plus 1 raised to 2/3. However, you see this? It's being squared. So the original expression for the u, you need to square it. So you see that one there. Okay? Now, 3 minus 3. Check, you have minus 3. This is u raised to 1/2. So what is u? Copy again. X plus 1, or quantity x plus 1 raised to 2/3, and it will be raised to 1/2. Because you see this, it's 1/2. So it's raised to 1/2. Plus c. The rest is simplifying this expression. So you have 3/4, you copy 3/4. 2/3 raised to 2 would mean that you multiply 2/3 by 2. By rules of exponents, it's now 4/3. Copy the 3 minus 3. And this one, 2/3 raised to 1/2 would mean that 2/3 will be multiplied by 1/2, which is 1/3. Because the 2's here will cancel each other. So that would be 1/3. So this is now the answer to the integral that you have before that is given, which constitutes, which requires us to do rationalization. This is now the answer. I'll clear my markings. This is your answer to this integral. When do you use this? Whenever your integrals involve this expression, determining the nth root of an x variable plus a real number, or an x variable with a coefficient other than 1, or a number multiplied to it other than 1 plus another real number. You will use this method. Any questions so far? Okay, so there is none. So we proceed. Okay, I'll go to method 2. So method 1 ato. So ano ang method 2? This is 4 integrals with mixed radicals. Mixed. Take note of this. Mixed radical. Our first example does not have a mixed radical here because you only have one radical expression. This one. X plus 1, if written in the radical manner class, if you write this one, the x plus 1 raised to 2/3, it would be written like this. And this one, it's the cube root of x plus 1 squared. So that's a radical. In method 1, you only have one radical. So, para hindi ka mo ma-confuse, isa lang diya ang radical. Okay? So this is the procedure that you will use. I hope everybody understand that this one is equivalent to this. That way you will say that you have a radical in this given integral here. Your radical is this one. Okay? Now I'll clear what I have written here because it will reflect in the next slide. In the next slide, what you will have is method 2 is mixed radicals. So not just one, but two. And they are not the same. So one is nth root, the other one is mth root. This could be square root, this could be cube root. This could be cube root, this could be fifth root. So mixed. As an example, you see here. Okay? So para you will distinguish right away what's the difference of method 1 from method 2. So you have the mix here. What will you do if you have the mixed radical? Determine first what's the exponent equivalent of the first. So this one has an exponent, this is equivalent to x raised to 1/2. This one is equivalent to x raised to 1/3. What do you do with the exponents? Look at here. The substitution equation that is used, so you also let u here or any variable that you want. The substitution equation now multiplies the exponents that you have. So this is 1/2 times 1/3. That's 1/6. This one, the sixth root, written like that, is also equivalent to that. Do you follow? So you already have your radical expression here. U is equal to x raised to 1/6. Just like what you did with method 1, eliminate this 1/6 because that's our problem. The rational exponent of your variables. Rational meaning fraction siya. The fractional exponent of your variable. So how do you do that? So now your expression is something like u is equal to x raised to 1/6. We want to get rid of the 1/6 because that makes things complicated for us. So what is the rule in method 1? Raise your substitution equation equivalent to the reciprocal of the exponent of your variable. Since this is 1/6, you raise it to 6. That's the reason why you have here u raised to 6 equal to x. You get it? You have now u raised to 6 equal to x. After you have done this, if this is the usual case, assign a variable for your original radical expression, raise it to an exponent, raise the expression to an exponent equivalent to the reciprocal of the exponent over your original variable. Next is differentiate. That is always your three-step procedure. Assign a new variable to your variable that is given, raised to a fractional exponent. Eliminate the fractional exponent by rationalization. This is done here. Next, differentiate. Don't forget this three-step rule. That is always the procedure. Okay, so differentiate. Our rule in here will give you 6u raised to 5 du. This one would be dx. What's the purpose of this? What do you think is the purpose of this? You will replace the x and the dx in the original integral by the u and the du. Okay? So this is what we're going to do. Okay? Now you have square root of x. It's written here square root of x is equal to, what is x? U raised to 6. And it's under the square root sign. In your algebra, u raised to 6 is equivalent to u raised to 6 raised to 1/2. Multiplying the exponents yields a 3. So that is why you have u cubed. In the case of the cube root of x is still u raised to 6. So you have u raised to 6 raised to 1/3. So 6 divided by 3. If you multiply, it's 6 over 3. That would be u raised to 2. So the square root of x you have here will be u cubed, and the cube root of x here will be u squared. The dx will be this, 6u raised to 5 du. Okay, so follow through. Square root of x is u cubed, 1 plus u squared. Cube root of x is u squared. Then the derivative dx is 6u raised to 5 du. Of course, you need to simplify first before you do anything that you need to do. Always simplify. So when you simplify, this 6 is written before the integral. You multiply the u raised to 5 and the u raised to 3. That would be u raised to 8 du, and you copy the denominator. If you look at this expression, which is a fraction, a rational expression, the degree of the numerator is higher than the degree of the denominator because this one is raised to 8, this one is raised to 2, then you need to do long division first. You're not going to integrate yet, but you're going to do long division. That way you can simplify further and then integrate your expression. Okay? Now, before I go to the next slide, have any question in here? Okay, Nan. Then I will proceed. So here. Remember, this is now our expression. We need to do long division. Let me check if the long division is shown here. It's not. So this is what we'll do. I'll show here long division. So you will have u raised to 8 divided by u squared plus 1. I'll just interchange. That way you'll know what I need to place here. So this should be u raised to 6 to make it a u raised to 8. So u raised to 8 plus u raised to 6. Okay? Multiply. So in the process, you subtract, you will have minus u raised to 6. Right? Now, u raised to 6 divided by u raised to u squared would be minus u raised to 4. So u and this would be negative u raised to 6 and then minus u raised to 4. When I subtract, I get rid of that. This would be u raised to 4. U raised to 4 divided by u squared would be u squared. Multiply again, you have u raised to 4 plus u squared. I have here minus u squared. For the last time, negative u squared divided by u squared would be negative, I'll just place it here on top, plus 1. So that would give you now, in here, you will have a u squared and you'll have a negative u squared, negative here, negative 1. So you have a 1. So what's your answer now? U to the 6th minus u to the 4th plus u squared minus 1 plus this remainder plus 1 over u squared plus 1. So the answer to this long division constitutes 5 terms, including the remainder. 6, 4, 2, negative 1, and this remainder, which is 1 over u squared plus 1. Okay? So take note of that, and that would be the answer that you'll be seeing here. Six, 4, u squared minus 1, and this is the remainder. Okay? Now, isn't this easier to process than the original? This is your original. This will be power rule, power rule, power rule, integral of a constant, and this one is the arctan. So we've discussed it last meeting, that du over 1 plus u squared yields an arctan of u. So you use power rule here, that would be u raised to 7 over 7. The 6 that you have here is written in here, okay? Constant. 4 becomes 5 divided by 5. 2 becomes 3 divided by 3. Negative 1 becomes u, and you have here the arctan of u. What is in the first place? U. What is this u? You go back to your substitution equation. Your u is equal to x raised to 1/6. Okay, this one, 6th root. Your u is equal to x raised to 1/6. So that's what you're going to do here. X raised to 1/6 times raised to 7 will be 7 over 6. X raised to 1/6 raised to 5 will be x raised to 5 over 6. And so on and so forth. You have here x raised to 1/6 times 3, or raised to 3 would be x raised to 1/2. U is x raised to 1/6, and this u is this, x raised to 1/6. This is your answer. This is your answer. You know that this is your answer because you now have the original variables given to you. Your answer rather is now in terms of the original variables present in the integral, the original integral. Do you get it? Any questions? Okay, no questions. Clear? Okay. The process of the third substitution, it's not anymore rationalizing substitution, but rather it's the topic of trigonometric substitution. This is quite a very long topic because you have to draw a triangle representing the trigonometric substitution that you use whenever you are given this particular expression. Okay, so for now, we will settle for this substitution, rationalizing substitution that we have covered. On Tuesday, we will discuss trigonometric substitution. And then proceed with the last topic, which is the method of partial fractions. Just check for tomorrow, or yes, tomorrow for the new problem set that I will be adding to the problem set that you have, because it's just until trigonometric transformation. I will be adding to it so that when you already answered all your problem sets, all you have to do to prepare for your exam is go through your problem sets again. That is already a form of practice and review. Okay? I'll stop sharing. Do you have